Good morning. This is section 12.3, inscribed angles. You have slides in a link in Schoology that you can find this very slideshow in color, so you could click through, and I encourage you to do that. There are a couple videos that will be helpful, and I'm going to flip through these notes pretty quickly just so that I can get to the examples to show you how those are done. So ultimately, through inscribed angles, we'll be able to answer one question. This is the Fitton Center for Creative Arts in downtown Hamilton. And the question is, where's the best seat in the house? And how can the knowledge of inscribed angles help us figure that out? So here's our goal, to be able to define inscribed angles and apply their properties to solve problems. So you see here a couple definitions, and you can write those down. This image is definitely required with those definitions, so you have a good visual. And we have a theorem, inscribed angle theorem. So you have the measure of an inscribed angle is half the measure of an intercepted arc. So this guy right here is going to be half this right here, and that's what this equation indicates. The measure of angle B is half the measure of arc AC. Now that's a new notation, so do be aware of that notation so you can recognize it. Measure of arc AC is how that is said. Theorem 1211. And then we have proofs. So you see this proof right here is a sample proof, and I actually have a copy where it doesn't say proofs in the middle of it. That's one of those things. You can click on this in the slides and actually see a little video clip, and here it is. And the theorem 1211 just points out that there are three different cases right here. This means center. This means O, the letter, capital letter O, is the center of this circle. And that's all that notation is meaning there. So here we have this angle, right, formed that goes right through the diameter. The diameter is one side of the angle. We have a case where the center is inside that angle, and then the inscribed angle where the center is outside. And so here's the proof of case one, and you'll prove the other two cases later. So just looking at this particular case, we want to prove that the measure of this arc right here, AC, is going to be half the measure of, or sorry, the angle here is half the measure of that arc. And the information that is given, circle O with inscribed angle B and diameter BC. So that is the given information. So sometimes you'll see in proofs that information or there's additional elements added to a diagram, and that's what's going to happen here first. We're going to draw radius OA, which you can see right here, dashed line, and all of a sudden we have an isosceles triangle here. You know what an isosceles triangle is? That's two sides congruent. So those two pink sides are congruent. It's an isosceles triangle. And therefore, OA and OB are congruent. And that another part of that definition would be to say, then also angle B is going to be congruent to angle AOC. Sorry, not angle AOC, but angle A, right here. Because these two congruent legs have opposite angles that are also congruent to one another, right? And that's by the isosceles triangle theorem. And you'll see in this proofs, this is just like in a courtroom where everything you say needs a statement to back it up, to justify the truth of that statement. And that's what proofs are about. And that's why proofs actually, you might not need in the real world to prove that the measure of the angle B is going to be half the measure of arc AC, but the process that we go through is so key in problem solving and just being able to substantiate claims with truth statements. Super practical. So here, measure of angle AOC. Okay, here, let's find it. AOC. That's going to be equal to the measure of A plus B. A plus B. Now, how does that happen? Why can we say that? Why can we make this statement? Well, because of the triangle exterior angle theorem. So, the triangle exterior angle theorem says, right, if we have a triangle outside, if we have an angle outside the triangle, like this angle right here is called the exterior angle to this triangle, it's going to be equal to the sum of the two remote interior angles, and that's the triangle exterior angle theorem. So that's legitimate to say because we've justified it with that theorem. Then the measure of arc AC is equal to the measure of angle AOC. The measure of arc AC is equal to the measure of angle AOC, and that's definition of measure of an arc. Okay, maybe you didn't know that one, but now you do. So we know that this is called a central angle if it hits where the vertex is the center of the circle, and that angle is actually equal to the measure of the arc. So stated here. Now we can actually substitute this angle, measure of angle B, and angle A. We can replace this right here with this right here, right? That's all that was done in this step, which is the claim, the justification for this statement is substitution. Alright, so then you can see how this keeps going. Wait a minute. Now we know that because B and A are congruent, that was stated earlier right here, because it was an isosceles triangle that was formed, we can replace A with measure of angle B since they're the same. So now we actually have two measure of angle B. So substitute and simplify. And then lastly, the last statement in a proof is always going to be your proof statement. And you can see they've actually just rearranged it around the equal sign, and that's okay to do because they're equivalent statements. So all that was done here is dividing each side by 2. Dividing by 2 is the same as multiplying by 1/2. So dividing each side by 2 is the justification statement for our final claim, that 1/2 the measure of arc AC is equal to the measure of angle B. So there's a proof. I'm not asking you to do this by yourself, but at some point in the near future you'll be able to do these on your own. So that's our proof. Check out that video from the link. Now we have an example. So find the measures of angle A and B. So angle A is, let's see. Looks like that's actually an arc. I apologize for that typo. I'll fix that on the notes. So the measure of arc A, let's cancel that. So arc. The measure of arc A, we know the relationship between this arc and this angle. Think about it. Based on our theorem here, we know that the angle measure is 60. This is kind of the reverse of this. If we multiply both sides by 2, we would get double. So this is going to be 120. So A is equal to 120, or the measure of arc AC equals 120 degrees. And then it asks us for B. Well, now for B, we have this angle right here, right where our legs are here, and the arc that's intercepted now is this whole thing, which we just need to add up. So 120 was the orange part, 30 is this little part right here, which is 150, and this time we're going in reverse. So B is going to be half of 150, which is 75 degrees, that's the measure of, well, that's an angle. Measure of angle B equals 75 degrees. So we have one angle that we needed to find and one arc that we needed to find. So angle, try to make a shortcut and how I wrote that, angle and arc. There we go. Alright, I'll fix it in the slides for you. So there's your first example. Now example 2, we have what is the measure of angle A. Now in this case you can see that we have a diameter that's associated with the angle formed here, right? We have an angle here. We're trying to figure out its measure. And you see the endpoints here. So the arc that is intercepted by this angle is all of this. And hopefully you're recognizing that as a semicircle. And a semicircle, well, hopefully you know that 360 is all the way around. So halfway around is 180 degrees. And therefore the measure of this angle would have to be half. So half of 180 is 90 degrees. And that's actually always the case when we have the diameter as one of the sides of a triangle. Then the opposite angle will be a right angle. So we can just label that as a right angle now that we know it. What are measure of angle A, B, C, and D? Whew. Okay, so angle D right here. We have to look at where that opens up to this arc AC, right? So that's 106 plus 100. So measure of angle, well, I started backwards, but as long as we get to all of them, measure of angle D is going to be 106 plus 100, which is 206, divided by 2, which is 103 degrees. Hopefully you realize that these need to add up to, well, it's a quadrilateral, so all angles add up to 360. So hopefully when we add up all these, the total, we don't get anything different than 360. Let's go, just go backward then. Angle C is opening up to, let's see, our endpoints are here and here, and we've got this side here, so 106 plus 64 is 170, and we have to divide that by 2, and so we get, let's see, 2 goes into 7 8 times, 85 degrees. And the measure of angle B then right here, hopefully you're getting the how this works. I shouldn't give them the same number of arc marks since they are not congruent. Angle B is opening up here to 64 and 90, so that's 154 divided by 2. So that's going to be 77 degrees. And I'd like you to try that last one on your own. So try and find the measure of angle A on your own. Last question says, what do you notice about the sums of the measures of the opposite angles in the quadrilateral in part B? So the opposite angles, which ones do we know? We know D and B. So let's look at D and let's look at B. What do you notice that those add up to? I just gave it away. So the measure of angle D plus the measure of angle B, well, that's going to be 103 plus 77, and that's 180, which we call that, we have a special name for that, hopefully you already have it, supplementary. So those are supplementary angles. Alright, now we have our corollary. And I have a page I printed out just so that the corollary isn't right in the middle. Again, I have a quick little video for you to watch about corollaries. Two inscribed angles that intercept the same arc are congruent. Okay, so corollary is just concepts that directly follow and are pretty straightforward from a theorem or from a statement of fact. So these are very closely associated with our previous theorem that we've already talked about. Okay? So if two inscribed angles that intercept the same arc are congruent, sorry, it doesn't say if, they are congruent. Which makes sense, because if we know the measure of this guy right here, it makes sense that since these two angles both open up to that same arc, that they would have the same measure, so they are congruent. Second, an angle inscribed in a semicircle is a right angle. Okay, so we talked about that. An angle inscribed in a semicircle, that's this right here. It's inscribed, it's drawn within the parameters of that semicircle. And this angle here is a right angle. Alright? It opens up to 180, a 180 degree arc, and half of that is 90. It makes sense. And third, the opposite angles of a quadrilateral inscribed in a circle are supplementary. We just showed that in the previous example. So each one of these was laid out in our previous example. Example 3. So we have here, angle 1 is inscribed in a semicircle. Okay, that's easy enough, so it's got to be 90. By corollary to, angle 1 is right angle, so the measure of angle 1 is 90 degrees. And that's all it asks us for. So that was pretty easy. Then in part B, we have, what is this, the measure of this angle? Well, it opens up to the same arc, right, as this triangle here. And since this triangle here has an angle of 38 degrees, this angle here also would have 38 degrees, which is stated here in our solution. In the diagram at the right, what is the measure of each numbered angle? Okay, so now we have to figure that out. You notice right away that they have created this diameter for us. So hopefully right away we notice that the angle 1 is a right angle, and as is angle 3. So we already know measure of angle 1 equals 90 degrees, and the measure of angle 3 equals 90 degrees. So now we just need to find 4 and 2. So 4, well, that opens up to this arc here. So that means this angle 4 is going to be half the sum of these two values. So 80 and 60 is 140. So the measure of angle 4 is going to be equal to 140 divided by 2, or 70. And we have one last angle to figure out. There's a couple ways we could do that, but the most direct way would be to use that corollary that says, okay, opposite angles, they're inscribed in this circle. This angle 2 has to be supplementary to angle 4. So the measure of angle 2 is going to be equal to 180 minus 70, which is 110 degrees. Does that make sense? Well, it's obtuse. Yes, that makes sense. So these are our 3 angle measures. And again, you could add these all up, and it does in fact equal 360 degrees. Here's another theorem. The measure of an angle formed by a tangent and a chord is half the measure of the intercepted arc. Okay, just some key phrases here. Tangent, so that's going to be this line right here, which it hits at exactly 1 point on the circle. That's definition of tangent. And a chord, that's a term that we're expecting you're familiar with. A chord is any inscribed segment in a circle with both endpoints on the circle itself. So this is a chord. So what's being stated here is that the angle formed by the chord and the tangent here is going to be half the measure of the arc that it intercepts, BDC. So half the measure of this arc will equal the measure of that angle. Okay, and you can see it drawn in 2 different ways, where the center is kind of within that angle, and the center on this first diagram is on the exterior of the angle itself. Works in both ways. So let's look at an example. Which arc does angle A intercept? Which arc does it intercept? So angle A, it intersects arc BCD. So we're going to write that. Arc BDC. And we can identify that as an arc because of the little curve that we put over top of those capital letters. So there's our answer for number 1. Which angle intercepts arc ABC. So arc ABC is here. So that would be angle D. So this is just a check for understanding. Maybe try the rest before you press pause on the video and try the rest before I do them for you. Which angles of quadrilateral ABCD are supplementary? So we know opposite angles will be supplementary. So A and C will be supplementary and B and D will be supplementary. So write that one in. And here's some vocabulary. Check. What is the relationship between an inscribed angle and its intercepted arc? Well, we know that the measure of this angle will be half the measure of the intercepted arc. So you could write that in here. Error analysis. A classmate says the measure of angle A here is 90 degrees. Well, let's see. Does that have, let's see, angle A is not the one, but if we had this angle B here, that would be a 90-degree angle because it is inscribed in the semicircle. That means both legs have points on the diameter, whereas in this case only one leg has a point on the one ray of that angle has points on the diameter of the circle. The other one doesn't, so that's where the error happens. Those are your notes. I think we've gotten through all of it, and this is a lovely colored picture in your slides, not in my printed copy here, but you will find that when you apply this theorem to our seating arrangement, we could sit right here in the center, but if this seat happens to be taken, we could also choose seats that would have the same viewing of the stage but be located in different spots. So good things to think about, applications of our inscribed angles.